In this video, we're going to talk about the substitution method of integration, and this really is one of the coolest things that we get to yet. It's the nitty-gritty of figuring out how to take integrals, and this is a technique that we'll use a lot. Really, it's the analog of chain rule for derivatives. So let's recall, how does chain rule work? Suppose I'm taking the derivative of the composition of two functions. I have this outside function sine, and my inner function is 3x squared. By chain rule, it's going to be the derivative of the outside function, which is cosine, evaluated at the inside function, which is 3x squared. But chain rule tells us that we also need to multiply by the derivative of the inside function. And you can go back to one of the previous videos to see a little more formal reasoning why we would need to have this multiply by the derivative of the inside function. This changing inside function affects the rate of change of this entire value. So recall, so this is the derivative of the outside function, and we have to evaluate that at the inside function, but we also have to multiply by the derivative of the inside function. So applying that to integrals, if we're going to integrate the cosine of 3x squared times x, this looks like something really messy, right? I have a product and I also have a composition of functions. But this product is exactly the product that we would need to say, aha, I know what the antiderivative of the cosine of 3x squared times 6x is. My indefinite integral in this case is exactly going to be the sine of 3x plus c. And that's because we just found what the derivative was up here, so going backwards, the antiderivative must be this. And notice each of these pieces are exactly what we want them to be. We have the composition of an outside function, and the derivative of the inside function is located there as well. Let's see a second example that goes over the same thing. So suppose we want to take the derivative of e raised to the power of x cubed plus 2. Again, by chain rule, it's the derivative of the outside function. In this case, the derivative of e to the x is just e to the x, but instead of x, I actually have this messy function x cubed plus 2. And by chain rule, I have to multiply by the derivative of that exponent. And that derivative is going to be, what's the derivative of x cubed is 3x squared, and the derivative of the constant 2 is 0. So that means if later on in life somebody were to ask you, I want to know what is the integral of e to the x cubed plus 2 times 3x squared dx, you could tell them what the antiderivative of this is, because we took the derivative and got here. To go backwards, we end up with e to the x cubed plus 2 plus c. And we have to have all of these special pieces in place. If I were, say, on my own, just asked, well, what about the integral of e to the x cubed plus 2 dx? And our answer to that question right now, and actually for a long time, is going to be question mark. That we apply this antiderivative or find this indefinite integral if we have both of these pieces, because chain rule applies in this case. So we have something formally written, and we're going to call it a U-Substitution. There's a pattern that happened in each of these places, that we have some, let's see, I'll show it to you this way. It's a composition of functions, right? We have an outer function and the inner function, and we also always had the derivative of that inner function multiplied. And we need those pieces because then chain rule applies, and our antiderivative is just the antiderivative of f evaluated in our function u. Let's see that with another example, and I'm going to introduce some U-substitution notation to make this a little easier. Let's look at this function and see if we can identify how to use our U-substitution rule to be able to solve it. I need to look for an inner function, and I also need to look for a piece where the derivative of that inner function is there as well. And in this case, I can see that x squared minus 1 I can think of as my inner function, and I'm going to call that u is equal to x squared minus 1. And the fortunate thing is that in this case, the derivative of u is right here. And I write the derivative of u, du dx. If this is u, the derivative of this is exactly 2x, right? And that's the piece that we wanted it to be. For our notation, however, to do this u substitution, we're going to treat these du's and dx's as differentials rather than Leibniz notation. It's a slight abuse of notation, but it's a caution to rewrite this instead of u dx equals 2x. I'm going to rearrange these differentials to write it as du equals 2x dx. And if you're uncomfortable with this, you can think of these as delta u and delta x, and this is a ratio of changes, and I can multiply them by either sides, and when taking the limits, they turn into these differentials. The subtle difference is, I'm doing this because I want to be able to convert this dx into the variable that I want it to be. So let's follow through with the technique. We did all of this work. Now I see that I can convert the pieces in this formula into some of the pieces in this formula. Namely, x squared minus 1 becomes my u variable. So the thing that I'm left under the square root is a u. And this 2x dx, those two pieces combine together to become my du. This is a variable change. Here I have a function of x's and I'm integrating with respect to x. I undergo this variable change. So now I have a new integration problem where I'm integrating with respect to u. And this is something that's easy to integrate. I can rewrite this u integral. U to the square root of u is the same thing as u. And I know how to integrate u to the 1/2. I can use power rule. I'm going to raise up the power and then multiply by the reciprocal. So this becomes u to the 3/2, because a half plus 1 is 3/2, and I multiply it by 2/3 plus c, right? I just did my integration. And I'd like to say, aha, this is my final answer, but this answer isn't quite good enough. My final step, so this was my integration step. In my final step, I have to convert the u back into its original. Comes 2/3 was u. U was just x squared minus 1. And I'm going to raise that to the 3/2. So after I integrate, plus c. Substitute back for x. Let's see another example of something similar, of something that we're going to try to do a U-substitution example. So let's say I want to take the integral of the cosine of x cubed times 3x squared dx. This is one similar to the one that we saw before. And I'm going to do the same type of process. What is my u going to be in this case? I see that the inner function, x cubed, I'm going to set equal to u, and it looks like I have the piece that I want, that the derivative, if u is equal to x cubed, I'm going to take the derivative of each side. The derivative of u I'm going to set as du implicitly, as implicit differentiation, and the derivative of x cubed becomes 3x squared dx. So notice that I have a u that I can plug in. I also have the du that I want, that these two pieces combine to make a du, and I can do a u substitution. So my u substitution, my first step, I haven't integrated anything. I'm just going to replace each of these pieces. X cubed becomes u, and 3x squared dx becomes du. And looking at this with fresh eyes is a new problem. We know how to integrate cosine. The derivative of cosine is negative sine, so the antiderivative of cosine is positive sine. So this is sine of u plus c. So my first step, I replaced my x's with my functions of u. Then I actually computed my integral, and then in my final step, so maybe I'll label. So my first step, I plug in u and du. In my next step, I integrate. And then in the final step, I need to replace my u values with my original x values. So this becomes the sine of x cubed plus c. So plug back in. And we can always check by taking the derivative of this using chain rule, and we see that the derivative of this would give us back what we wanted. So here's the hardest u substitution that we're going to do. It's my last example of this kind, and then we're going to talk about what it looks like to work with definite integrals rather than indefinite integrals. So it looks like my inner function in this case is 5x plus 1. So I'm going to equal to 5x plus 1. And that means that my du, taking the derivatives of both sides, my du is equal to 5 dx. I took this side derivative with respect to x. And the problem is over here, I don't have a 5, so I would need to make a 5 happen in here, and I have this extra x. And this is the problematic piece. What am I going to do with this extra x? It's nice when I have a u and my du takes care of whatever function of x that happens to be floating on the outside out here. And in this case, I don't have something to take care of it. So I'm going to need to do some additional steps. And I'll write my additional steps over here in green. Maybe I'll take care of the 5 first. So the 5 we know how to take care of. That I can say, aha, this is the same thing as the integral of 1/5 times 5 times x times the square root of 5x plus 1 dx. And so I have a 5 dx that this piece combines with this piece to make the du that I want. Du. 1/5 can be put out front of the integral. 1/5 times the integral of x, and I can change my square root of 5x plus 1 to be the square root of u, but I still have this x floating around here. So this is where I have to do my scratch work. And in this, it's sort of a special case that this is a linear relationship between u and x. So I can solve from one variable to the other. Namely, I can say, aha, if u equals 5x plus 1, that means u minus 1 equals 5x, and it means that 1/5 u minus 1/5 is equal to x. And I can use this substitution back in for x, right? This arrow might make it confusing. And so I rewrite my integral in this case to be 1/5 times the integral. Instead of having an x here, I want to be able to integrate all with respect to u. This x becomes 1u minus 1, and the square root u I'm going to rewrite as u to the 1/2 du. And you ask, why is this any simpler than what I started with? I did all of this work, I did these u substitutions. The reason why is that on this I can do the distributive property and end up with a polynomial with rational exponents. Whereas here, you can't distribute this x into this square root because this isn't actually a square root of x. It doesn't distribute into these terms. These aren't just... But that means that doing just a little bit of algebra, I can distribute this and I end up with 1/5 u to the 3/2 minus 1/5 u to the 1/2 du. And this is something I know how to integrate. This is going to be equal to 1/5 of, I'm going to raise the exponent, this becomes u to the 5/2, and I have to multiply by 2/5 times 1/5, because that was the original coefficient, minus u to the 3/2, I'm raising the value of the exponent by 1. I'm also going to multiply by the reciprocal, multiply by 1/5 plus c. And multiplying all of this out, I see that this becomes 5 times 5 is 25 times 5 is 1/25 u to the 5/2 minus 5 times 5 is 25 times 3 is 75 2/75 u to the 3/2 c. So this is about the trickiest type of u substitution that you can find, one in which once you do the u substitution, you have to solve for this extra variable that's just hanging out there. The final thing that I want to talk about is what to do with definite integrals. So far all of these examples indefinite integrals, one where we didn't have bounds. This is an example of one where we do have a bound, and our method is going to be very similar. One thing that I like to do just before I get started, notice that I'm integrating with respect to x, and so these bounds are also numbers that relate to x. This is the bound from when x goes to 1 to x goes to 2, and when we change to a new variable, we need to keep that in mind. So let's proceed the way that we always have. First, I'm going to have to identify what is my u and what is my du. And in this case, it works out pretty nicely. It's hard to sort of identify what is the innermost function, and I see later x squared plus 6x plus 1. This whole thing is being squared, and the derivative of it is 2x plus 6. And that's not exactly what we have, right? This is close, but not quite. So I'm going to do a little algebraic manipulation to get this numerator to look like what I want it to look like. And fortunately, it's something that I can actually just factor out a 2 from the numerator. This is 2 times 2x plus, in the later I factored out a 2 from the first term, and I factored out a 2 from the second term, so that it aligns perfectly with what I want for my u substitution. So now that I've factored out that piece, let's take the pieces I need. That 2x plus 6 dx forms my du. In the numerator, I still have that 2 hanging out there. In the denominator, I'm left with u squared, because this whole thing is u squared. And here's where the bounds come in. Here's where they are tricky. And we have two different options. Maybe I'll write out my options, that these bounds are in terms of x, but now my variable is in terms of u. And we need to have the bounds need to match the variable. So what are we going to do? Well, we have a couple of options. One, let's change these bounds to be in terms of u instead. And what relationship do we have to do that? Well, we have a relationship between u and x. So here we see that u is equal to x squared plus 6x plus 1 if x equals 1, which is the lower bound. We get that u equal to 1 squared plus 6 plus 1, which is actually just 8. And if x equals 2, which is the upper bound, we see that u will equal to 2 squared is 4 plus 6 times 2 is 12 plus 1, which is 17, right? So making sure that I did that correctly, we have u being equal to this function of x. So if x is 1, I can plug 1 into here to find out what my u value will actually be. That when x is 1, u is 8. When x is 2, u is 17. And that means that my new bounds, and I'm going to write them as u equals 8 to 17. So finishing up this integration, I actually like to write negative exponents. I'm going to write this as 2u to the negative 2 du as u goes from 8 to 17. Gosh, and this is something I can't do in my head. So when I integrate, I raise the power by 1, and so I'm going to end up with u to the negative 1, and I multiply by the reciprocal of the exponent, which the reciprocal of negative 1 is just negative 1, so I end up with negative 2 times u to the negative 1. And I'm going to evaluate that as u goes from 8 to 17, which means that the upper bound is negative 2 times 17 to the negative 1 minus negative 2 times 8 to the negative 1. And I can simplify this greatly by saying this is negative 2 over 17. Minus a negative is a positive 2 over 8, which is 2/4. And I could simplify this fraction, but I'm not going to for this example. Great! One way to deal with definite integrals. I'm going to show you a second way to deal with definite integrals as well, and we're going to do the same examples so that you can compare them side by side. So let's look at the same example. The integral as x goes from 1 to 2 of 4x plus 12 divided by x squared plus 6x plus 1 squared dx. We're going to do the same thing that we did before. We're going to pick our u to be equal to x squared plus 6x plus 1. Our du is going to be equal to 2x plus 6 dx. We're going to do that same manipulation that we did before to be able to get our U-substitution. 2 times 2x plus 6 divided by x squared plus 6x plus 1 quantity squared dx, evaluated as x goes from 1 to 2. Again, I'm going to pick out the pieces of my du. I have a 2x plus 6, and I have the dx. Together, those make my du. So I'm left with the integral of 2 over du. This piece and this piece are my du remains, and this interior function becomes u squared. And I'm going to do something that textbooks don't like. This is the thing that I like to do. I know that this is as x goes from 1 to 2, and I know that this variable is a u, but I'm just going to leave it as x. So I recognize that the bound is different. But I can still integrate, and I'll show you how I correct the problem. So I'm going to do my integration, because I can integrate this. This is the integral as x goes from 1 to 2 of 2u to the negative 2 du, which is, let's compute this integration. This is the integral, again, it becomes negative 2u to the negative 1, evaluated as x goes from 1 to 2. Notice this x doesn't match this u. I can't plug it in. I recognize that the bound variable is different. So in order to be able to plug it in, I'm going to use the same technique that we did before. And that technique is, I know what u is. U is this big, long, messy thing. So I'm going to plug that in as x squared plus 6x plus 1 to the negative 1, evaluated as x goes from 1 to 2. So what is the difference? So the difference in this method is that I do the integration. After I integrate, before I plug in the bounds, I plug in the variable. And this is what that we don't leave our integral in terms of u. We want to go back and make sure that it's in terms of x. So that's what I'm doing here. I went in and I made it in terms of x. And now I can evaluate this. And it turns out this looks a little messy. The negative 2 times, plugging in 2 here, I get 2 squared, which is 4, plus 6 times 2, which is 12, plus 1. So that's 4 plus 12 plus 1, which is 17, to the negative 1. And then I subtract off my lower bound. I'm subtracting negative 2 times 1 squared plus 6 plus 1, which is 8, to the negative 1. And simplifying this, I get negative 2 17ths minus a negative 2 eighths, which is the exact same answer that we got before, just using a slightly different method.